Hello, everyone. Welcome. Thank you for organizing such a wonderful day. My name is Shubhanshu, and I will be talking about CAP Theorem and how you can use CAP Theorem for your telemetry data or specifically your telemetry pipelines. I know the title is big and huge and it talks about a lot of things, but I'll try to simplify and keep it very simple. So a little bit about me and my company. My name is Shubhanshu. As I said earlier, I'm a software engineer at a company called Sawmills. I've been working with observability solutions for 6-7 years. Previously to Sawmills, I was working at Adobe as an observability engineer, managed their metrics and tracing platform. Also, Sawmills is a startup. We just came out of seed round and we just announced publicly. We are a smart telemetry management platform. We use AI as well as all the new technologies to help you make more sense of your data and to intelligently cut your costs. I'll take a pause. You haven't missed anything. It was just my introduction, which you can get by with. So anyways, so getting back to the talk, today we are going to be talking about CAP Theorem, and CAP Theorem as in how you can use CAP Theorem and concepts and the CAP Theorem methodology to implement your telemetry pipelines and how you can optimize the distribution of data across your platform. Who here has run into issues with their observability bills, no dashboards, and you name it, all the different buzz and jazz which comes with it. And we all know what is the source of this. The telemetry volumes, which are being generated by applications, be it logs, metrics, traces, profiles, you name it. And why have these problems become so prevalent in the last few years? Main reasons: we live in a distributed systems world. We have applications which try to communicate with each other in a microservice environment. We have IoT devices. We have applications which are growing at exponential numbers and every day increasing. To give you some numbers, smaller organizations generate about 1 terabyte of data per day. And when you go to large organizations, the amount of data just go to petabytes and maybe more than a few petabytes in a single day. And that's massive. That's a huge scale. And when we talk about this kind of scale, we run into a lot of different things. It's not just the cost to store this data. You run into different storage issues. Do you store it in hot tire? Do you store it in other tires? You run into network issues, your network costs. Finally, it becomes complex to manage such a wide environment, such a wide platform. And with so much data, there is always the decision. Is this the right log line? Is this the right metric? Do I need this? How do you find the correct use case for the tool which you are using? And here comes a new perspective or an existing perspective or concept which is being used in the distributed systems world for a while. CAP Theorem states, for people who might not know, CAP Theorem states you can only have 2 of the 3 core principles with you all the time. The 3 principles are consistency, availability, and partition tolerance. Talking in simple terms, consistency means the data which you are seeing on one node is on one device is same as the data on the other side. That means the data is, you can read the data. A simple example could be you logging into your bank account and seeing the right balance or seeing the number. Availability, again, very simple concept, allows you to look at the data or get the data back or look at anything back and get the response back without getting errored out, without getting timed out and things like that. And partition tolerance. We live in again, as I said, distributed systems world where applications talk to each other, where applications communicate with each other and there is an underlying network, which is sometimes not in our control. You will have delays, you will have timeouts, you will have those things. And so partition tolerance is non-negotiable. I know I talked about it in terms, but if you want to look at simple examples, partition tolerance is very tricky, but a simple example is you go to a bank, you own the bank, you own your account, and you want to visualize your balance. You should be able to go to any branch of the bank when the main network between the communication network between different branches is broken. You should still be able to work with that particular bank. So Our goal today is to think about CAP as a mental model or a framework when designing our telemetry pipelines, and think about those trade-offs, how it makes more sense for our business and our use cases. We won't be applying all the principles as rigidly as it is being applied in the databases or in the database world. So we talked about the CAP theorem. Now, switching gears a little bit, how can we apply those three policies in the telemetry sense? C can stand for consistency or data correctness, which means that the data which is being sent from your application to the backend is accurate, is accurate, and you are seeing the whole truth. None of the data is being lost as part of your transit, and it reflects the reality of your things. Like, for example, talking in terms of traces. The entire trace which you are seeing, is it complete? Am I missing individual spans? Same goes for your alerting and metrics. Like, you want your SLOs to be always as accurate as possible, because that's where your SLAs are defined upon. And finally, sometimes for compliance reasons and security reasons, you got to make sure your data is complete and you have everything what you need. Availability. You want to make sure your applications can send the data to your agents, observability agents, collectors, whatever you're using, to capture all that information and send the data to the backend. They shouldn't be running into issues because of a number of reasons. They shouldn't be crashing. If they are crashing, your application data might be lost. And we want to avoid that as much as possible. We also want to make sure that my application is able to connect and send the data to basically the agents are able to communicate with the backend and send the required data. Finally, partition tolerance. Partition tolerance in telemetry is essentially your system should be able to operate when there are network delays or when there are issues in the underlying infrastructure. Simple example, again, your app should be able to communicate your collector or your agent, and the agent vice versa to gateways or backends, whatever, how you have configured things. And why it matters? Because we cannot build a system which doesn't have retries or buffering, because the network will have issues. And we got to think about that and keep that in mind when building such a system, so that we are able to send and communicate the data. And you can think about your system in such a way that, for example, when you are building such a system, can my application or my agents run without communicating with each other, or without, when there is an issue with my telemetry backend or my infrastructure, will they be able to sustain themselves? And as I said earlier, partition tolerance is non-negotiable. The only two things you have to play with are always availability and consistency. And it's a game of trade-offs. As I said, partition tolerance will happen, network issues will happen. And now you have the decision to make. Should you prioritize consistency or correctness of your data, or you ensure your system is available, your telemetry pipeline is available, and it can accept the data and send it to the backend? Again, both the choices have a specific trade-offs. When you prioritize consistency, you might risk the infrastructure, like it might not be able to handle the load, it might have delays, it might require a lot of buffering. And when you build it for availability, that means you'll have to sample, some of the data might get dropped, and so you might have inconsistent data or some data loss. Again, as I said, there is no magic bullet. It depends on your infrastructure, your business needs. So how can we implement this today, and what can we do today with the existing solutions available? The best choice, obviously, is OpenTelemetry and OpenTelemetry Collector. I bet most of you must be familiar with OpenTelemetry. If not, with 2 minutes, OpenTelemetry is the second biggest project under the CNCF umbrella, and it has SDKs, agents, and all the things revolving your telemetry data. And specifically talking about the OpenTelemetry Collector, it's like a vendor agnostic agent as well as a telemetry collector, and it allows you to receive the data and transport it to your telemetry backend of choice. And the key components in the collector are receivers, processors, exporters, and connectors. But for this talk, we are going to be focusing mostly on the processors, because at the processor level, we can implement our choices of consistency, availability, and partition tolerance. So partition tolerance can be implemented at each layer individually, but we are going to be focused on mostly on the processors. And there are some key processors which you can read about, but again, I'm not going to go over individual of them right now. Let's talk about logs. What can you do with logs? And what is the biggest problem when it comes to logs? With logs, it's the volume. The amount of volume which from your applications is just enormous. And when you get so much of logs, you have to make the decisions. What do you do with this much data? Do you send it to your backend, everything in the most indexable and the hot storage, or do you send it to different layers of storage? Again, no magic bullet. You got to decide based on your application and team needs. Maybe you can filter certain data out. Maybe you can trim certain attributes which you don't need, which in terms help you to enhance your availability of the system. But again, as I said, it will impact the consistency or correctness of the data. Another strategy, sampling things or having quotas inbuilt, which allows you to block certain things. We will be talking about quotas a little bit. There are a lot of strategies on the backend side as well, like all your vendors support some kind of limits as well as tiering and all the other things. Talking about metrics. Now, in metrics world, everybody must have heard about the high cardinality problem or nothing but the unique labels. The unique label combinations for a particular time series, which leads to enormous growth in the amount of data you are capturing. And you end up paying so much bills or your costs, observability costs, just because of a tiny label somebody added. Again, you all know, and you might have been there and with this, and this impacts your dashboard load times. It impacts your observability of the entire system. So what can we do to deal with this with thinking about CAP in mind? Again, you can do filtering. You can do transformation by making use of the existing available processes in the open telemetry connector. Not a lot of work, just for some fine tuning, just some kind of aggregation at the collector level before sending it to your backend. That allows you to have obviously the telemetry pipeline being available, and it does impact your consistency, but it's a choice we got to make to get the right data or to sacrifice the data. And obviously, there are options of recording rules, which you can do at the agent level, as well as the collection agent level, as well as the backend. And finally, as I said earlier, the same thing applies. The telemetry backend will have choices for you to do tenant-based segregations and limits and things like that, but that's at the final layer. Finally, tracing, which is one of my favorites and the most challenging one. With tracing, the problem is how do you sample the trace data to get the correct information you need, as well as not to pay the high bills which you might be paying. Talking about the collectors, again, there are two lovely, amazing processors which are available to us, which can help make the decision, do we prioritize consistency or correctness of data, or do we prioritize availability of our system? Simplest one, the probabilistic sampler, which is again a concept of head-based sampling, which allows you to only collect a particular trace, but that means you might not get the rich data or the traces with errors because it's random. It's based on a mathematical equation, which is not the thing probably you want. Tail-based sampling, which helps you to get the good data. It allows you to look at the complete trace before making the right decision. Do we want to sample it? Do we want to keep it? But again, it has impacts on your collector performance. You got to do a lot more buffering on the collector. You might need more resources to run those things. So again, the choice depends on the business needs. Finally, can we think about sampling or this sampling in a different way, which we have talked about all the telemetry signals? Can we implement some kind of policies or quotas at the collector level, which ensures your applications can send data, but keep the collector always running, do a fairness guarantee between multiple tenants when you run in a multi-tenant environment? Sorry. It's okay. Because of a tenant, because of a noisy neighbor, we don't want our entire telemetry pipeline to go down. So can we do something on the collector level, which will allow us to do some kind of enforcing, which will ensure our agents are able to communicate and send the data to the backend. Again, collector already comes with one of the such processor which does those blocks and limits. It's again the memory limiter, which is very essentially allows the collector to run even if they prevent itself from memory related crashes and things like that. You can build it easily on top of any of the filter processors. You can add the limits as part of the filter processors, which can enforce some rules, custom rules for your organization, which will only allow to send certain things. And finally, you can build something novel of your own or a custom processor, which shares the state with the entire fleet and allows you to do this in real time by looking at the entire data set before sending it to the backend. I'm going to be talking about the third point a little bit more in the next slide, where we go over it. And finally, you do have the option of doing the control at the backend level, where you have a bunch of controls provided by your tool of your choice. So this is a very simple architecture diagram of how a quota managed application might look with OpenTelemetry collector as core, with a shared state-based concept, and how you can send the data to your observability backends. Obviously, on the left-hand side, we have all the sources which are responsible for generating all your telemetry data. In the center two blocks, we have our core components of the collector, the receivers, the processors, the exporters. And finally, on the right-hand side, we have our telemetry backend of choice or observability backend of choice, and an optional sync where you want to send the filtered out data if you want. And finally, you have your management or control plane, which has the configuration related to all the quotas, rules, and all those things. As I said, in the center where we have as processor, can we build a custom telemetry quota enforcer or a processor which shares the state across the collector fleet, which allows you to apply those rules in real time, which also helps you to, now again, it's not going to be perfect. It's going to be eventually consistent because it's sharing the state across the collectors. That means you might send a little bit more data than the rule, but it will always keep your system available. It will prioritize availability of the collectors over consistency of the data, because again, quotas are nothing but drop rules or rules which allows you to filter things. Finally, a little bit more about the quotas and their trade-offs. As we said earlier, quotas are nothing but the policies which allows you to define certain behavior when that system needs to perform when it reaches a certain threshold or a limit. They act as a barrier on your collector level to prioritize the availability of the infrastructure and the entire pipeline. They prioritize the availability of the entire fleet with the impact to the consistency and the completeness of the data. You can do a lot of things with this kind of processors. You can, again, as I said, you can drop certain things and send those things to a tiered storage for rehydration and things like that. You can configure a learning on top of it when a certain quota is hit, so that the engineering team owners they can take a particular action based on that. And finally, this system should be able to work in a partition tolerant manner. That means if a collector is not able to connect to the fleet or any other connectors as part of the system, it should continue to work, even if that means we're sending more data to the backend. We don't want to break the system or stop sending things to the backend. With that said, what are the key takeaways? We talked a lot. I know I spoke a little faster, but if you want to take something out of this talk, think about the CAP Theorem as a framework. It's a framework to make the right decisions based on your data, based on your environment. You got to choose between availability and consistency of the data. OpenTelemetry, as I said, OpenTelemetry is the way to go. A lot of this is already available. You can just go use the open source tooling and integrate in your infrastructure, and you will have almost all the features which I talked about in-house without putting it enough effort and running it on your own. The strategies to manage are always sampling, filtering, transforming, playing with your data, using quotas, and designing the architecture to keep your pipeline always running. And finally, AI on ML. Now, again, there is just a lot going on in the AI ML world, but maybe you can build something novel over here as part of one of our processors, which allows us to look at the data in real time and create those rules or analyze them before sending it to the backend. That allows us to save the cost, network cost, that allows us to enrich the data and only send the right things and save us money in the long run. With that, thank you. And I open the floor for questions.